During a brief equipment test, before it was even fully operational, a new observatory spotted over 11,000 previously unknown asteroids in just a few weeks. If a simple calibration exercise catches that many unseen rocks, it reveals the true scale of what we've been missing. We live our daily lives surrounded by a massive cosmic blind spot. That test was conducted by the Vera C. Rubin Observatory, perched high in the Chilean Andes. It was built specifically to look into those shadows. We are beginning to fill in the blank spaces on our map of the solar system, replacing a reliance on lucky sightings with a growing inventory of our cosmic neighborhood. For decades, astronomy has mostly relied on looking at the sky through a narrow straw, studying one tiny patch of darkness at a time. The Rubin Observatory opens a wide-angle window. The heart of this facility is a 3.2 gigapixel camera. This payload is designed to capture the entire southern sky every few nights. The space around our planet isn't getting more crowded. Our vision is simply becoming sharp enough to register the rocks that have been circling us for billions of years. This leap in optical power changes our relationship with space, moving us from passive observers to active sentinels. Near-Earth objects, or NEOs, are notoriously difficult to track. They frequently slip through the gaps in existing sky surveys. These rocks evade us because they are small, their surfaces are dark, and their orbits often approach us straight out of the blinding glare of the sun. Masked by daylight, a rock can cross millions of miles of deep space unnoticed, building extreme velocity. By the time it clears the sun's rays and enters our field of view, it could be minutes away from our atmosphere. That leaves zero time left for evacuation or deflection. In planetary defense, the primary risk is determined by visibility. A threat we haven't detected is the only one we have no way to stop. We know exactly what that looks like. In 2013, a meteor strike over Chelyabinsk, Russia, provided a visceral reminder of our vulnerability. A 20-meter rock detonated over the city with the force of an atomic bomb. Because it approached from the direction of the sun, no telescope saw it coming. Current tracking networks are effective at finding massive, extinction-level asteroids, but they can still miss objects on the exact scale of the Chelyabinsk meteor. Surviving in this solar system without comprehensive sky mapping depends on the statistical probability of a miss. It is a strategy based on luck. This is why finding 11,000 new asteroids in weeks is a massive victory. A comprehensive catalog of space rocks provides a crucial tactical advantage. This chart displays a web of predicted asteroid paths. Once we identify an object and plot its trajectory years in advance, a collision becomes a predictable equation. With repeated observations, a blurry estimate of where a rock might be tightens into a precise, predictable line. In astrophysics, tracking equals preparation. It transforms random cosmic events into preventable hazards. We have already tested the solutions. NASA's DART mission proved that we can use kinetic impactors to slam into a threat and nudge it off course. Kinetic deflection is a straightforward problem. It requires exactly two things: years of advance warning and hyper-accurate orbital data. That is the role of the Rubin Observatory. Its data output feeds the warning systems that make physical defense possible. By mapping these hidden trajectories, we are shifting from a passive existence in space to an active strategy of monitoring and security. We are finally paying attention. We are turning a vast unknown into a map we can read, predict, and ultimately defend against.